Hello everyone, my name is Pedro Mortazavi and I'm a PhD candidate at the University of Toronto working with Professors Osang Kwan and Konstantin Christopoulos. The project also had an industry partner, specifically Dr. Mike Gray from Casconix. So I'm going to start off my presentation with a bit of background on the hybrid simulations that we did, then I'm going to move forward to the reference structure, the experimental setup, and at the end some results and conclusions. So let's start with the cast steel yielding connectors. Its developments is really the topic of its own, but really it's a yielding damper that uses steel casting technology, and it was developed by Dr. Mike Gray about a decade ago at U of T and is currently being commercialized at Casconix. Since its development, it's been implemented in a number of building projects in North America, and the way it works is that it's assembled into the frame in series with the brace. So as the frame deforms laterally, these parts that are referred to as the finger or yielding finger would bend back and forth and would dissipate the seismic energy. Also, the fingers have a triangular shape, and that means that they would have a uniform curvature and would have simultaneous yielding. Because of geometric nonlinearities, the yielding connectors develop an increased post-yield stiffness at large deformations. And given that this mechanism is complex, modeling yielding connectors is not very trivial. So currently, there's an OpenSea's material referred to as the cast material, which is typically used for modeling the yielding connectors. And we wanted to see whether this material is adequate, and the best way to do that is to perform hybrid simulations. So for our hybrid simulation communications, we use the University of Toronto simulation framework. And really what it is that it's a framework that facilitates multi-platform simulations using a suite of programs. And also we would have experimental modules, which enables the users to have experimental physical substructures in pseudo-dynamic hybrid simulations. So for instance, if you have a special concentrically braced frame, you can have the whole building in open seas, but you can have the first two braces or however many you want modeled in Abacus and capture the response more accurately. Or you can have them in the lab and test them physically. In the project that I'm talking about right now, we use the University of Toronto hybrid simulation platform as the experimental module, and we used OpenSeas as the integration module. So I'll talk a little bit about the UT10. One of the criticisms that hybrid simulation often receives is the limited number of physical substructures that we can test in the lab. The rendering that you see right now shows the University of Toronto shell element tester. A few years ago, my supervisors were looking at this thing and they asked themselves, why not use these actuators to increase the number of physical substructures in hybrid simulation? And that thought led to the development of the UT10s. So really the UT10 consists of 60 hydraulic actuators in a very unique configuration, which enables us to test different specimens in different configurations. In its current form, we're able to test up to 10 elements which are loaded uniaxially. And it's a self-equilibrating system. Typically, the top actuators are used to apply the external command. The bottom actuators are used to counteract those forces, and the out of plane and side actuators are typically used to support the system. So this is a picture of the UT10 with 3 scaled BRBs, which are tests that we did with my former colleague, Dr. Saeed Mojiri. And this is the control station of the UT10, where we control the UT10 actuators, we control the middleware program, and so on and so forth. So moving on to our hybrid simulation. The reference structure was a 4-story steel building with the yielding brace system, which was designed in downtown Los Angeles. So in the north-south direction, we have 4 yielding brace systems, which are shown here. So we took one of them, we detailed it, and note that we are using the stub beam connection, which is shown to have the highest level of ductility. And another overview of the design. And these are the sizes of the yielding connectors that were used in the first floor, second floor, third, and fourth. After that, we needed to have good numerical models, both for our purely numerical studies as well as the hybrid simulation. So this shows the global modeling assumptions. I'm not going to get into the details, but I'm just going to say we made sure that our models are as robust as possible. We modeled all the connections and obviously all the elements that have the potential of yielding. We also use the cast material that I talked about to calibrate the yielding connectors. The information about this is provided in the paper, so you can refer to that. The other important aspect in hybrid simulation is the substructuring strategy. That basically means what elements you're going to physically test in the lab. Those are referred to as the substructure, and what elements you're going to model numerically, which is known as the integration module. In these tests, we had the luxury of using the UT10. So naturally, we tested all the 4 yielding connectors that really drive the overall response of the frame in the UT10, while the rest of the structure was modeled numerically. We also had to select a number of ground motions. We had a suite of 40 ground motions. We took 3 of them for the hybrid simulations. So this is a time-lapse video of the first hybrid simulation. First, we did 2 MCE records back to back. So this is the brace on the first floor, yielding connector on the second, third, and fourth, and these are the hysteretic responses. We also have the view of the yielding finger on the first floor. So this is the first earthquake. Appreciate the increased post-yield stiffness as the yielding connector is pushed into large deformations. So I'm going to skip ahead to the second earthquake in the interest of time. And in the second earthquake also we get the same post-yield stiffness on the other side. So these experiments were followed by a third MCE earthquake, which I'm not showing here, but the link is here on YouTube in case you were interested to watch the video. So the results are provided in the paper in detail, so I'm not going to go too much into the details, but I'm just going to say that using these experiments, we were able to find a number of discrepancies between the numerical model and the experimental results, which would be missed in calibration to cyclic test results and would affect the results. So to summarize, we believe experiments such as this would be useful for identifying the limitation of numerical models, better calibration of numerical models, and calibration of ultra-low cycle fatigue life models. Some references for this presentation. Also, the work that I talked about was recognized by the Multi-Hazard Engineering Collaboratory on Hybrid Simulation in the 3-minute thesis video competition. Specifically, we were the winner in the novelty category, which you are welcome to watch the videos there. So with that, I would like to thank you for your attention, and I would be happy to answer any questions that you might have. Thank you.